Welcome to this podcast as we continue our discussion of NMR. So let's go to the next slide. Although there have been conflicts between faith and science over certain issues, I do not believe that faith and knowledge have to be in conflict. That is a good thought. Okay, today in this podcast, we're going to talk about the chemical shift, relative positions of proton NMR signals, characteristic values of chemical shifts, and diamagnetic anisotropy. Get that pronounced right in a minute. But first, let's talk about the chemical shift. The chemical shift tells how far the signal is from the reference signal. The positions of the signals in an NMR spectrum are defined according to how far they are from the signal of the reference compound. Tetramethylsilane, sometimes we call it TMS, is the most commonly used reference compound. It's very volatile. It will disappear very quickly from samples. The reference point of an NMR spectrum is defined by the position of TMS, and we give that the number 0 parts per million. This is a methyl group right here. So it's a silicon atom with 4 methyl groups surrounding it. Since the methyl protons of TMS are in a more electro-dense environment than are most protons in organic compounds due to silicon being less electronegative than carbon, the signal for the methyl protons of TMS is at a lower frequency than most other signals. So it appears to the right of the other signals. In fact, we give it 0. Of course, carbon is more electronegative than silicon, and so will attract the electrons more than silicon will. The chemical shift is a measure of how far the signal is from the reference TMS signal. It is determined by measuring the distance from the TMS peak and dividing by the operating frequency of the instrument. Since the units are hertz divided by megahertz, a chemical shift has units of parts per million, ppm, of the operating frequency. Most proton shifts fall in the range from 0 to 10 parts per million, so you'll see that as the range on the NMR spectra. The proton NMR spectra for 1-bromo 2,2-dimethylpropane shows the chemical shift of the methyl protons is at 1.05 parts per million, and the chemical shift of the methylene protons is at 3.28. Notice that low-frequency upfield shielded signals have small chemical shift values, or delta values, whereas high-frequency downfield deshielded signals have large chemical shift values. And here's our compound, and protons in this methyl group, this one and this one, are equivalent, and then we have the methylene protons on that carbon. So these are A, generate the peak at A. Call this A. We'll call this B, and these 2 protons cause this peak. And why is this peak intensity higher? Of course, it's because it represents 9 protons of the 3 methyl groups, but only 2 methylene protons are represented by this peak here. The advantage of the delta scale is that the chemical shift of a given nucleus is independent of the operating frequency of the NMR spectrometer. It's factored into delta as the denominator. The above table here on this slide helps you keep track of the terms associated with NMR spectroscopy and serves as a summary at this point. Over here on the left, protons sense a larger effective magnetic field, so come into resonance at a higher frequency to the left. To the right, protons sense a smaller effective magnetic field, so they come into resonance at a lower frequency. And you might envision TMS right here, all the way to the right. The chemical shift is independent of the operating frequency of the spectrometers. Ours is 90 megahertz. They go all the way up to 300, 400 megahertz. But yet we can compare one NMR to the other because of this fact. The relative positions of Proton NMR signals. Okay, here's an interesting slide showing 1-nitropropane. In the case of 1-nitropropane, there are 3 signals because the compound has 3 different kinds of protons. These 2, these 3, these 2, these 2. So there's 3 different groups. The closer the protons are to the electron withdrawing nitro group, the less they're shielded from the applied magnetic field. So the higher the frequency at which their signals will appear. The protons closest to the nitro group has a signal at 4.37 parts per million. The ones furthest from the nitro group show a signal at the lowest frequency of 1.04 parts per million. So you can see what's going on here. Okay. The closer the electronegative, the atom or group, the more it shields the protons. All right, here we've got display. The electron withdrawal causes NMR signals to appear at higher frequency at larger delta values. And this is just illustrating that we have different halogens attached to the same string of carbon atoms and protons. Here's iodide, bromine, chlorine, and fluorine. Of course, iodine is the least electronegative, fluorine is the most electronegative. And notice that the frequency, the NMR signal for this group of protons is higher than it is for this one over here. So the position of the signal depends on the electronegativity of the halogen in the molecule. The more electronegative the halogen, the higher is the frequency of the signal. The more electronegative the halogen, the more de-shielding occurs. Okay, here's some characteristic values of chemical shifts. This table here is table 15.1, and it gives various protons are highlighted in these molecules, giving you an idea of what the approximate chemical shift will be. And all the way from methyl protons, 0.85, of course you could put on this chart TMS, which would be 0, and then all the way, if you follow this all the way down here to this amine group that that's causing de-shielding due to the electron withdrawing of the adjacent carbonyl group to these protons on the nitrogen. So you have a wide spectrum of values of chemical shifts. Here is a slide showing the NMR labeling convention for proton groups in compounds using 1-bromopropane. And this is a convention that we use for talking about the spectra in regards to the structure. And you can see we labeled these groups of protons A, B, and C. And A has the lowest frequency. It is the least, it is shielded, and B and then C is the closest to the most electronegative atom. It has the highest frequency and is de-shielded. So in the molecule, lowest frequency signals generated, the least de-shielded on this side of the molecule, or shielded. And then C is the highest frequency given, and it is the most de-shielded. Here are NMR signals for various compound groups. There's actually 7 regions of the NMR spectrum, of which one is empty right here. There's no example given. Each of these is an approximate value of the chemical shift for different kinds of protons in various molecules, as you can see in this table. Table 15.1 has more values, and the study guide and solution manual has many more in a table that's in the manual. So you can see here on the left we have electron withdrawing, and so we have de-shielding of the protons that are close by. The protons are in an electron-poor environment. Here's a carbonyl group and another carbonyl group. So we have de-shielding, downfield, high frequency, large delta values, whereas over here on the right, protons are in an electron-dense environment. They're shielded, upfield, low frequency signals, small delta values. Okay, since carbon is more electronegative than hydrogen, the chemical shift of a methine, as you can see here on the left, is more de-shielded and so shows a chemical shift at a higher frequency than the chemical shift of methylene protons. The chemical shift of methylene protons is at a higher frequency than the chemical shift of methyl protons in a similar environment. So note, the methine proton is a hydrogen bonded to a carbon that is attached to 3 carbons. Methylene protons are hydrogens bonded to a carbon that is attached to 2 carbons. Methyl protons are hydrogens bonded to a carbon that is attached to 1 carbon. And as a result, we can see the difference in the shift. Okay, relative positions of signals. The proton NMR spectrum for butanone gives 3 signals, marked A, B, and C, the groups of protons that cause that. The signal for A protons is at the lowest frequency. The A protons are farthest from the electronegative withdrawing carbonyl group than any of the other groups of protons. The B and C protons are the same distance from the carbonyl group, but C protons give a higher frequency signal than the B protons because methylene protons appear at a higher frequency than do methyl protons in a similar environment, as we saw previously. Remember, by convention, the set of protons responsible for the lowest frequency signal will be labeled A, the next set will be labeled B, and then the next C, and so forth. Now, in 2-methoxypropane, the A protons give a signal that is the lowest frequency because these protons are farthest from the electron withdrawing oxygen. The B and C protons are the same distance from the oxygen, but the signal for C protons is at a higher frequency because methine proton appears at a higher frequency than do methyl protons, as we saw earlier. Okay, one last topic, diamagnetic anisotropy. Let's look at the next slide. This is an example. Hydrogens bonded to sp2 carbons have chemical shifts at higher frequencies than predicted by the electronegativities of the sp2 carbons. As in this slide, a hydrogen bonded to benzene, the benzene ring, appears at 7.3. A hydrogen bonded to a terminal sp2 of an alkene appears at 4.7. Hydrogen bonded to a carbonyl carbon appears at 9.0 parts per million. The unexpected chemical shifts of hydrogens bonded to carbons that form pi bonds are due to diamagnetic anisotropy. This term describes an environment in which different magnetic fields are found at different points in space. The chemical shift of protons attached to the sp2 carbons appear at higher frequencies than one would predict. When a magnetic field is applied to a compound with pi electrons, the pi electrons move in a circular path. This causes an induced magnetic field itself. This field affects the chemical shift of the proton. The protons resonate at higher frequencies than they would if the pi electrons had not induced a magnetic field. So hydrogens attached to sp2 carbons have higher frequencies than if they did not. So diamagnetic anisotropy describes an environment in which 2 different magnetic fields are found at different points in space. And we're talking about the applied magnetic field and the induced magnetic field. And notice here that induced magnetic field is in the same direction as the applied magnetic field in the region where the protons are located. So they're in the same direction. This causes unusual chemical shifts for hydrogen bonded to carbons that form pi bonds. The protons show signals at higher frequencies because they sense a larger effective magnetic field. And here's another example of this. The pi electrons of an alkene or an aldehyde also induce a magnetic field that is oriented in the same direction as the applied magnetic field. So these protons also show signals at higher frequency than expected. Induced magnetic field is in the same direction again as the applied magnetic field. And one last example right here, however, a hydrogen bonded to an sp carbon produced a chemical shift at a lower frequency, about 1.9 parts per million, than you would predict from the electronegativity of sp carbon. This occurs because the direction of the magnetic field induced by alkynes cylinder of pi electrons in the region of the proton is opposite to the direction of the applied magnetic field. As a result, the proton senses a smaller effective magnetic field and so shows a signal at a lower frequency than it would if the pi electrons did not induce a magnetic field. And you can see right here that it is in the direction opposite, going this way, as opposed to the direction of the applied magnetic field. That concludes our podcast for today.